Hi, Darshan. Hello, sir. How are you doing?
Hi, how are you? Fine.
I'm doing well. I hope you're fully recovered.
Yeah,
Very good.
it is 3 months now already.
Right. I know it's been 3 months. It was such a surprise when I heard
Yeah.
from you. You were going through.
Your volume is so low.
Is it? Let me fix it.
Yeah,
One. Is it any better?
slightly better.
Yeah. Hi, Arpita. Hi, Kartika. Hi, Darshan.
Hi Hardik. Hi Narendra sir.
Hi, Darshan. You have raised your hand. Go on. You can unmute yourself and share your thoughts.
Sir, it was a mistake. You can go ahead, sir. No problem.
Okay, now we're waiting for everyone to join in. We still have 4 more minutes to go.
Kumar sir. You are on mute, sir.
Good evening, all. Good evening, Mr. Hardik. Good evening, Mr. Narayan.
Good evening, Sukumar.
Very good evening, Mr. Sukumar.
Yeah.
We still have a couple more minutes to go, but in the
Yeah.
meantime, if there are any questions that we can address, Darshan, Alankrit, we're very happy to address. If you want to introduce yourself, we can get this conversation started. Okay, so we'll give it a couple more minutes before everyone comes in. Hi, Harish. Good evening. Arpita, we are at the top of the hour. Should we get this started or should we give it another few minutes before we get it started?
Let us wait for another 1 or 2 minutes. We are waiting for Sir Krishna Murari, sir.
Okay. I also see very few participants. Yeah, so maybe give it another couple minutes. Hi, Naveen. Good evening. Good morning, rather. I think you're mute, Naveen.
Hello,
Hi, Naveen. Very good morning.
good morning, good evening to you all.
I think, Arpita, in the interest of time for everyone who's joined, let's get the session started. There may be a few people who may be joining along the way, but let's go ahead and get this started.
Yeah, so Krishna Murari, sir, will be joining. I just spoke to him.
Okay,
So
no
let's
worries.
Good evening, everyone, and a very warm welcome to all of you. On
Yeah.
behalf of AeroDef Nexus, I'd like to thank you for joining us for today's webinar, Ask Me Anything on Composites. It's wonderful to see such enthusiastic participation from students, young engineers, and professionals across the country who are keen to explore the world of composites, which is one of the fastest growing areas in aerospace and defense. AeroDef Nexus intends to be an aircraft OEM over the long horizon. Our first aircraft program is ARX-1, 2-ton payload fully autonomous vehicle for cargo and ISR applications. To support the development of this aircraft program, we are in process of establishing the thermoplastic composites facility. In order to meet our workforce needs as well as the larger industries need, we have launched Composite 101 training program led by experts who are on the panel today. We intend to offer practical, case-driven, hands-on learning and development through this course. Top 5% participants of the course will also have an opportunity to intern with us at AeroDef Nexus. We are truly honored to have a few distinguished experts with us today. First is Mr. Hardik Someshwar, founder and CEO of AeroDef Nexus, also an ex-Poolings Aerospace, who has been guiding our initiative to upskill aerospace talent and bridge the industry academia gap through specialized training programs. Then we have Mr. Shukumar, former executive of HAL, is a composite specialist who brings over decades of experience in composite manufacturing and structural development for aircraft and helicopter programs. He is trained abroad in composites manufacturing by reputed aircraft company. Our next speaker is Dr. Krishna Murari, a former AGM at HAL, With 38 years of experience in aerospace composites, quality and manufacturing, a PhD holder with multiple patents and a Raksha Mantri Award recipient, he has played a key role in ALH and LCA composite programs and now works as a technical consultant on composite air taxi development. We are honored to have him with us today. We are delighted to welcome Mr. M.S. Narayan, an aeronautical engineer with decades of experience in helicopter design and composite blade development. He played a key role in ALH, LCH, and LUH composite blade programs at HAL. We are honored to have him with us today. It's a privilege to welcome Mr. Naveen Rastogi, founder and principal consultant at 3P Composites LLC, with over 40 years of experience and a PhD from Virginia Tech. He is a globally respected expert in composite materials and structures. He has authored over 75 technical publications and is an associate fellow of AIA. We are honored to have him join us today. We are pleased to welcome Ms. Kavita Bhandari, Head of Training Academy at AeroDef Nexus. She leads the development of industry-aligned aerospace training programs with a strong focus on practical skills and workforce readiness. We are delighted to have her join today's panel. Together, they will help us understand why composites are transforming the aerospace industry. With that, I will now hand over the session to our moderator, Mr. Hardik Someshwar, who will take this discussion forward. Over to you, Hardik.
Thank you so much, Arpita. I really appreciate it. And thank you, everyone, for joining this session. Again, a warm welcome to the session. We've curated one of the highly respected panel today. So here's the plan for the day. What we will try to do is take about 35-40 minutes of curated session based on some of the questions that we've got from you, as well as the area of expertise that all our panelists have. And at the end, we would be very happy to take any additional questions that you may have. So we should have a total of about an hour. And at the end, we'll also introduce you to our full-blown Composite 101 course that's kicking off from 17th of January. So without further ado, let's go in and get the conversation started. Before we go into details, we have several experts on the call. I would like a quick opinion from each of you, starting with Mr. Narayanan. Why is composite such an important skill? What do you see as a job potential? What do you see as the potential for future young engineers in the composites business? What are the opportunities out there?
Good morning, good evening, everyone. When Hardik asked me to make a framework of this course, see, I have experience of about 3 decades on composites in HAL. Actually, composites started in 1950s in Europe because the price of the oil was increasing. So the aviation industry has to spend a lot when they make aircrafts with metals. The aircrafts also has to carry large number of passengers, but metal application made them very heavier. So they wanted a material which makes the aircraft structure lighter. And at the same time, it performs in the different atmospheres, in different weathers, at different altitudes, different temperatures, like that. So the development of composites was a necessity for the aviation industry. That's why a lot of aviation industries jumped into research on composites. Slowly, the composites found use in other industries as a spin-off in automobiles, helmets, tennis rackets, cycles, and everything. So nowadays, composites are used in so many applications, mostly military and civil aviation industries. So the necessity is the fuel price hike is the driver for composites. Then also, when you use metals, For example, in helicopters, the helicopters have got a very complex set of hinges. We call it hinges for the blade to move around. So those hinges are made out of bearings, seals, which require continuous maintenance, like greasing or oiling, something like that. And they have fixed life. People wanted to eliminate those hinges and reduce the weight of the rotor hub of the helicopter. In that direction, Germans have invented a full composite rotor blade, which was the first blade on a helicopter. So like this, the use of use of composites have spread into everything where weight reduction and performance is required. It went into even rocket structures also.
Thank you,
This is a
Mr.
simple
Narayanan. Really appreciate your perspective. I'm just gonna, in the interest of time, I'm gonna, go to a couple of next set of panelists. Mr. Narayanan already talked about why composites were invented and how widespread the application of composites is. Next up, Mr. Sukumar, what do you think are the skills, most needed skills for young engineers and working professionals to be able to get jobs in the area of composites? What do you think are the most important skills? Is it just theory? Is it practical learning? Is it CAD? Is it, is it manufacturing? What are the roles that are most in demand, and what opportunities exist out there based on years of your experience?
Hello, good evening all. Comparing to the other manufacturing processes like machining, sheet metal forming, welding technology and all, composite stands out in the sense one can start off in all other areas after the college education. Whereas in composites, if you really want to put in your efforts and start off involving, then you need some kind of exposure and training in addition to the exposure given in the college. That's a specialty of composites. Basically, the skills required for composite is any mechanical engineer, that way, an engineer from any discipline can easily pick up, provided he has some fundamental knowledge in computers and software packages, especially required for a designer. So, and for a manufacturer, some kind of exposure in the theoretical exposure is required to appreciate the and respect the process of manufacturing. The theoretical background is required, and that can be obtained by any of such trainings given here. And in addition, after once you get exposure to the theoretical, you get an edge in the job market to compete with others who have come from the college fresh. And the skills further required are only the blueprint reading. Once you learn the blueprint reading of composites and understand the materials, what are the composite materials and what are the properties of the materials, and what are the applications of these various composite materials in different situations. So once this is understood, it can the glide will be very smooth, and one can pick up. And regarding the market, the huge market is open in the composites field, and it's an order of the day that new companies are coming up in the manufacturing of composites. So there is a big job opportunity for the people who are interested in the new field like composites.
Thank you, Mr. Sukumar. Next up, I would go to you, Naveen. What do you think are the top applications? Not all of our participants may know. What are the major applications in aerospace and defense industry of composites? And since you spend most of your career in designing and analyzing the structures, if you can highlight some challenges and opportunities in designing these structures, that would be very helpful. You're on mute, Naveen.
Thank you, Hardik. Yeah, and pleasure meeting all the panelists here. Um, yeah, composites have seen a tremendous growth. As I think Arpita mentioned, that I've been working since uh, 81, kind of when I started working on, kind of got introduced to composites. So it has seen tremendous growth. I mean, applications are now everywhere, starting from sports industries to all the way, I mean, starting from aerospace, obviously, to all the way to the sports industries now. Aerospace, obviously, there are a lot of, initially starting with motor cases and then moving on to a lot of equipment racks, which is what I worked in 1981, actually, for SLV. And then later on, moving on to to the aircraft industry, particularly, starting with, I mean, we can go back all the way to the wooden wings, but more talking about advanced composites. We started with, actually initially we started with a lot more control surfaces, where fairings and control surfaces provided a lot of weight reduction. And obviously, as one of the panelists mentioned about the maintenance part of it, which is also a key part of why composites are being used, is because they're non-corrosive, they're pretty much corrosion resistant, which is one big thing in many of the applications, which aerospace, marine, boats. So a lot of those things kind of drove the growth of the composites. Uh, Moving on into, particularly, late last century and this century now, when Boeing particularly spearheaded the campaign to start working on commercial plane, which is all composite. So, and before that, obviously, the I would say the foundation was built by the defense industry, where bombers, some of the military aircraft, fighters, and others, they started using composites in a high volume. So essentially, the real reason is really the strength to weight ratio and the low maintenance costs. And also some of the complex curvatures and the structures which we can now design and manufacture using composites, that was not possible with metals, particularly if you are doing titanium or aluminum, particularly titanium for military aircrafts, for the applications. Titanium is not the easiest metal to work with when you start get into manufacturing of it. So that's where the composite starts to show up, as an alternate material initially, to start kind of producing some of those complex curvature parts using carbon fiber, or even boron epoxy, if you recall all the way back to 80s. I mean, there was a lot of applications where boron epoxy was being used. So they're now obviously moving on to, as I said, to commercial planes. I mean, there's 787, and then the one I have on my screen is a 350, which I worked on. So there's so much. They're almost 50% by structural weight. I think that's what the many data points out there. But there's almost 50% by structural weight is composite there. The whole wing, the fuselage, the empennage, and not just the fairing, not just the tertiary or secondary structures, the primary structures, what we call, are being now made out of composites, and particularly carbon fiber, glass, and now moving into some of the natural fiber biodegradable composites in non-aerospace applications. I would say has been seeing a lot of growth. So it's a pretty exciting field to be in, and with the many opportunities to really make career in the field of composites. Thank you. Thank you.
Thank you. Thank you so much, Naveen. Dr. Krishna Murari, I would like to hear your perspective. And you've been not just, doing composites, but you've been also teaching a lot of different topics. You've been writing books. So I would like your perspective, and specifically, if you can share insights about how's the, quality aspects or not, repair aspects of composites different than the, regular metallic structures.
Good evening, everybody. This, as far as quality aspect is concerned, so it is quite different from metallic. Say metallic people inspect at the final stage after machining. Only few stages in between if there are some critical dimensions to be checked. And we can check finally without in between inspecting that parts. But that is not the case in composite. Starting from incoming inspection till final tagging, every stage is at most important from inspection point of view or quality assurance point of view. Because we are not only making the component, we are really making the material itself by making the layup a different orientation to provide the strength whatever we need in what directions. This we tailor making the properties in composites, and if we don't maintain the orientation properly and layup sequence properly, then definitely we'll going to land into problem. Not only layup, after layup, there are many stages of vacuum application for pre-compaction at various stages. If those are not followed and inspection not checked thoroughly, we may lead into problem of voids or foreign objects inside the layup and leading to delamination and different kind of defects like porosity and other things. In addition, the atmosphere environment where we do layup, that also to be controlled, and it become responsibility of the quality to see that environment is controlled. After final layup, again bagging is another important aspects. If that not done properly, it may get busted or leak may start during curing in autoclave, and that result in total failure of the component and being material costly. We may lose lot of money on that and delay also in the project. So another aspect comes from quality is that stage also. Then again comes test specimen manufacturing and quality checks like NDT, non-destructive inspection also very important part, and lot of patience is required, analytical approach skills are required, and in addition to that, the person should be good at reading the drawings, understanding the composite total process, and parameter has to be controlled. So a quality person should have that kind of skills. When those skills are there, then a lot of training also required as far as NDT is concerned, like ultrasound inspection, even tap test is a quite important part. Starts from that. Then we have X-rays are there, we have C scan, we have CT scan, we have X-ray. So many important things are there in quality the person should know. And first of all, you should know theoretically what are the aspects of those various methods for inspecting the composite panels or composite component, and what are the effect of various materials like carbon, Kevlar, or your glass, and also orientation effect, difference between unidirectional and bidirectional. All those things person should know. And when layup is carried out, when there's a complex surfaces are there, how important is orientation? Say 5-degree deviation in orientation result in 30% reduction in the strength. So quality becomes utmost important to check and guide the employees who are doing the layup. They may not be that perfect on reading the drawings and on some time. And people sometimes appoint those technicians at a lower salaries and all. So that thing should be done. So these things are required for a quality, and a lot of scope is there for quality people, because that getting a good quality person is composite very utmost important and required. So I like to that much. Thank you.
Thank you, Dr. Krishna Murari. Okay, so just to highlight, there are multiple roles that one can get into, right from R&D to design and analysis of a composite structure, manufacturing of parts, production supervision, quality, repairs. There are a bunch of different possibilities, and for each of those roles, you need specialized skills. So what I'm going to try and do now is, go a bit deeper into some of these roles. And again, I would come back to Mr. Narayan. Mr. Narayan, if you can share some anecdotal examples about the rotor blade design, the challenges, what was your design approach, and what was your design philosophy, and more so, what do people need to learn if they want to be good designers?
You see, the application of composites in a helicopter rotor blade is a very complex one. Why composites came into helicopter blade is there are two reasons. One is, as I mentioned in the introductory description, the helicopter rotor is a specially moving beam around a hinge through which it is attached to the hub of the helicopter. The center portion where the rotor blades are attached to the helicopter is called hub. That hub accommodates all the motions called flapping, which is vertical motion, which requires a horizontal hinge, and there's a lead lag motion. It is in the plane of the rotor around a hinge axis, which is a vertical hinge. All these hinges in the metallic regime are made by very strong needle bearings. Whenever you apply a bearing, you require very fine fit, very fine machining of the components, and good lubrication and proper assembly. And the number of components increases because of this. So one bearing means there will be so many things. There will be a seal, there will be a arrestor, there will be some circlips for keeping the bearing in position. So there are a lot of loose parts which come into picture. Designers actually wanted to eliminate that because we wanted to reduce the weight of the hub. At the same time, we should handle the loads, flapping loads, lead lag drag loads. Lead lag load is drag load, and torsion loads because of the aerodynamic environment in which it operates. So how to do that? So they utilized glass fiber. By using glass fiber, they created a hinge. It's called a virtual hinge. The advanced light helicopter, what is developed in HAL in India, what we have developed from 1980s, it is called a hingeless blade. It doesn't have hinges. That means it has got virtual hinges. It is made up of composite materials. The composite materials are aeroelastically tailored because that layup itself is special. It is aeroelastically tailored in one such region of the blade called the collar, wherein all the motions and loads of the blade is accommodated. It's a very complex subject to read. It will be, I don't want to go deeper into it, but with that, we could reduce the number of components from, say, 250 components in one branch of a blade. It will come to some 20. You can see the amount of parts reduction. That's why, because of the reduction of parts, reliability of the system increases. So if you purchase an helicopter with a metallic blade and metallic hub, you may have to do a lubrication inspection, an X-ray inspection, or any CT scan inspection, or a visual inspection, something called tap testing. All these things are done say every 500 hours. And they have got some life because metals have got fatigue. Because of fatigue, the life of the metal is limited. Life of the blade becomes limited. So, a metallic blade, the life will be approximately 2,500 hours to 5,000 hours maximum, not beyond that. But whereas with composites, if you purchase one helicopter for your use, say, you need not have to replace the blade for throughout the life of the helicopter. Because the life of the helicopter is approximately 20 years. In 20 years of the helicopter use, if someone has to change 4 times the blade, you imagine the running cost for him. It will be terrible. So with composites, we can almost achieve infinite life. That is a life which is comparable to the life of the airframe itself. 20 years, you can use a blade. Unless the blade is damaged by some use, terribly damaged, won't be repaired, we can use the blade because it is fairly damage tolerant and repairs can be done at the spot of the customer. It need not have to be brought to any service station or so mobile repair kits are available nowadays. So even in the on top of Mount Everest, you will be able to repair a blade composite component. So to that extent, repair methods have been made. Some equipments are also have been devised. So that is one use of composite in rotor blades. Another use of composite is if you see designers see if you want to increase the lift of the blade, aerodynamic designers thought of using different shapes of aerofoils. That is the cross section of the blade is called an aerofoil. So there are various aerofoils which can give you higher lift, low drag, and a favorable pitching moment characteristic. If you don't know about pitching moment characteristics now, just forget it. But very good pitching moment characteristic is required, especially for helicopter blades, because it has to be controlled by the pilot. It should not impose too much of load to him when you want to pitch the blade. So that is there's an approximate explanation of about pitching moment. So when you want to vary the airfoil, the surface of the blade changes a lot, which cannot be fabricated with metallic sheets. Metallic blades are made with skins which are formed, sheet metal which is formed. Such a thing is not possible. So changing the airfoil is not possible. And moreover, the twist of the blade varies high in the nose, high in the root to low in the tip. That means it is called a nose down twist. A nose down twist for the angle of attack is pre-built into the blade for producing proper lift at the center of the blade. To achieve that, aerodynamics have thought about non-linear twist. So if you have to incorporate non-linear twist, it cannot be made out of metal at all. It can be piecewise linear, but it cannot be made perfectly smooth non-linear twist. It follows a non-linear equation. So to use that type of to make that type of blade, which gives a very optimal lift and pitching moment characteristic, you need to employ composite materials only. There is no other way.
Thank you, Mr. Narayanan. It shows all the passion and hard work that would have gone into designing a structure. I'm sure you can talk for hours or days altogether. But again, in the interest of time, I'm just going to continue to keep this session going. I'm going to come to you, Naveen. When you want to analyze a composite structure, what are the main tools do you need and what are the criterias? How do you analyze a composite structure? Is it different than metallic structure? Is the damage tolerance different? Is the static different? What should someone learn if someone wants to be a very good composite analyst?
So yeah, I would start with the tools first. So because a lot of folks want to learn the tools right away. So tools are pretty much over the time, over I would say last 4 to 5 decades, have been kind of modified to cater to the analysis of composite structures. I mean, be it Abacus, be it Nastran, which are finite element analysis tools. Uh, ANSYS is another example, or there are many others like that, affiliate tools. So there are many tools now which have been modified or enhanced, I would say, to cater to the composite analysis. Now, going into the analysis of composites, obviously, I would say this way, the basic equations of plates and shells haven't changed. But the key thing in composites is the anisotropy and orthotropy and anisotropy later, depending upon the layup and the angles. So those are the key things to take care of and understand in the theory of composites, particularly, or mechanics of composite materials. And then I'll again maybe focus more on the practical side of it, is when you analyze metals, you're pretty much looking at some principal stresses and von Mises stresses and things like that. But in composites, since they are multi-layered structure, you have to go and look at the stresses and strains, particularly strain. If the failures criteria are strain driven, then you have to go look at all those, I would say, numerical values and parameters, and understand each layer. Think of, 20, 30 layer panel. For example, a 350 wing or some primary structures have almost that many layers in some cases, particularly near the splices. So if you think of those, and now you want to understand in each layer what is going on, because the failure criteria are applied are applied layer by layer. So you need to understand the stresses and strains in each layer, and that creates a high volume of numerical data. So one of the biggest challenge when I worked and mentored people is particularly they know the metal, they want to learn the composites. One of the biggest challenges to understand the high volume of data. While the tools will provide you that, but post-processing that and understanding that takes some time. So that's one of the biggest in composites is you need a lot more patience to understand and process the data. And this is just static analysis I'm talking about. Fatigue is another domain. Good thing and bad thing, as one of the panelists, Mr. Naran talked about it just now, is fatigue is kind of gets hidden behind the damage tolerance in composites. So what I mean by that is, since the composites are already designed to be damage tolerance, most particularly I'm focusing on the advanced aerospace composites like carbon fiber, then what happens is if you're designing them for damage tolerance and the effect of defect, which again another panelist mentioned about quality. So those, once you consider those kind of things, which are also important to consider in the analysis of composites, then essentially the composites do not see much fatigue related issues after that, because your strain or stress levels are kind of much below the endurance limits. If you think of metal terms, are much below the endurance limits of typical carbon fiber, carbon epoxy structures. So volume of data, understanding the failure theories, and obviously mechanics of composites and anisotropy, understanding the different failure theories, environmental effects, which is a big thing, which is kind of most of the time and almost all the time when you talk about titanium and aluminum and steels, they are not as prominent and right up there. But in composites, moisture absorption, degradation due to UV rays and temperature effects, particularly mismatch of temperatures between metals and composites if you're making a joint together. So joints is another important aspect of understanding how metals are joined together versus how composites are joined with composites and composites are joined with metals. So those are all important aspects of learning composites. The tools are out there. The big companies like Boeing and Airbus and many other companies, they have developed their in-house tools, which are kind of their trademarks. So there are because when we deal with, particularly, I'm just concentrating a little bit more on the commercial and business jet aircraft design side. You have tens of thousands of, basically they're like 3 to 4, 5,000 load cases you're analyzing at a time. And those load cases, you look at, again, go back to simple example of 30-ply panel, you have 3,000 load cases to analyze. This volumes and volumes of data, basically. So that's why there's a lot of automation has happened over time. I mean, it was not there 30, 40 years ago, even 20 years ago. But with the use of more and more use of composites, the companies have invested in developing composite analysis specific tools. And actually, if you guys online are interested, my website is there, www.3pcomposites.com. There are many tools I have put in there for analysis of composites. So I would say those are the specific things come to my mind. Design is another aspect when you get into the design of composites. How to drop off the plies, how to taper the plies, and particularly to take care of the interlaminar stresses, which is not again a metallic thing because there are no multiple layers in metal. It's one solid piece of metal thickness. But in how we build composites, thickness is through the putting number of layers together. So between each layer, then there is stress field called interlaminar stresses. That's another key aspect to understand about composite, is how those interlaminar stresses then affect the overall behavior of composites and the failure of composites. So I think that's a pretty good summary, I would say, about design and analysis of composite. Obviously, I always say devil is in the details. There's a lot of things to learn, but that's where the training courses comes in.
Thank you so much, Naveen. Going up to Mr. Sukumar. Mr. Sukumar, what are the primary methods used in aerospace and defense for manufacturing these composite parts? And what are the typical challenges have you seen? And how have you dealt with these challenges?
Mentioning about the various processes that employed in making the composite products. The hand layup. Hand layup consists of wet layup and pre-preg layup. Wet layup is nothing but
There's a lot of echo on your line, sir.
There is a lot of echo.
Yes.
I don't know why.
You may have to just reduce the volume of your computer. Thereby, I think the echo should go away.
Yeah. Hello?
Yeah, go on, sir.
Hello? I think it's okay, no? No.
Are you connected on two devices? Maybe you're connected on two devices, which is why we are hearing a lot of
I have switched off my mobile. It's not. I'm
okay,
on the
perfect.
laptop.
I think you're good now. Go ahead, please.
Yeah, I switched it off. Okay. There are various processes like hand layup, wet layup, pre-preg layup, and filament winding, out of autoclave process, resin transfer molding, and vacuum assisted resin transfer molding, VARTM. Coming to the hand layup, there are two methods. One is wet layup method and pre-preg method. Wet layup method, you drape the dry fabric on the mold layer by layer and add liquid resin onto it and spread the resin uniformly and build the layers to the required thickness and carry out vacuum bagging and cure it in room temperature. You don't require any equipment like autoclave or oven or any of such equipments. It's purely cured under vacuum in room temperature. So it is a low cost production method wherein design inputs can be obtained for the development purpose. Fairings, cowlings, brackets, and simple products like that can be made out of wet lamination method initially for the prototypes. and later on we can switch over to pre-preg manufacture. Simple toolings are involved for wet lamination. That's how it is preferred in the initial stages. Um, then coming to the pre-preg layup. Pre-preg layup, there is the same mold is used, whereas the material used, raw material used is pre-preg, pre-impregnated material. That is fiber reinforced, pre-impregnated with resin already by the manufacturer and partially cured to B stage. And it is supplied to the user in the form of rolls. So it will still have a lot of tackiness so that the pre-preg can be cut layer by layer and can be positioned on the mold, and it can be laid up using the hand. And so these two methods are all labor intensive. And after completing all the layers as per the required thickness and orientation, which is very important, orientation, like plus 45, minus 45, 0, 90, these are the various orientation that is used. And finally, vacuum bagging is carried out. And the whole thing is cured in an autoclave. So in pre-preg method, you need an autoclave, which is an expensive equipment where the parameters like temperature, pressure, vacuum, and time are all controlled. So what are the challenges involved are in this hand layer? It is purely labor intensive. So there can be a mistake in the orientation of the layers, which is very expensive, as Mr. Narayan just explained. Yeah, and Mr. Krishna Murari also explained that a small change in the orientation leads to a huge reduction in properties. So orientation can go wrong unless it is supervised and the technician is trained. Secondly, the layers, the overlap between the layers has to be maintained properly. If it is not maintained, it will lead to thickness buildup in that area. It will show up in the inspection stage. And other things are vacuum bagging. Vacuum bagging is very important. If vacuum bagging is not done properly, it will affect the final product. It will not get cured, and it will degrade the properties, mechanical properties of the composites. So these are the various areas wherein we need to concentrate, as it is a manual labor intensive method.
Thank you. Thank you so much, Mr. Sukumar. In the interest of time, I'm just going to move on and just ask one final question as part of the prepared content and then take the questions from the audience. Dr. Krishna Murari, can you talk at a very high level about various repair methods? Because repair of composite structures is also different than metallics. So can you please shed some light on repairs?
Sure. One thing already Mr. Narayan has told about the repair in field. So very
Yes.
important part of composite that we can repair wherever our aircraft is there, helicopter is there. But there are various repairs methods are there. But basically, you see that before going for repair, one important part is there. We have to check the damage, how much is there. So usually, if say metallic is there, your damage is very, very clear, open. If cracks are there or something like that. But if something drops on composite outside, sometime you will not find any damage, while internal layer would have got damaged. And if it is not properly checked during regular checks, if small dent also we should thoroughly check. It may result in failure of the component. So there are various repair schemes are there. Depends on what kind of damage is there. If it is a superficial outer layer is there, you have to check by maybe various method like tap test and A scan and all. And superficial layer, if you was top layer you want to check, you have to have proper NDT method. One is tap test, another you have to do ultrasonic by through transmission because pulse echo will not able to catch it. After getting that, if it is a deeper layers, there are various schemes, various methods that specifically three, four types of repairs are there. Either we can cut the damaged portion and carry out the layers and additional layers above that. And we can do either wet layup or as he told this Mr. Sukumar about the pre-pack layup, and we can carry the curing kit there and cure that. So one is that. Another, we can have a doublers. We can put the doublers and do the layer and bond it. Another can be injection of the resin. So, and core if it damaged, how to replace the core. Another repair repair things are there. We have to remove the core, put another coat, apply the layer both the side and cure it. So there are various ways depends on what kind of defect is there. And that way we carry out the layup, and designers help also required to find out the what of the original strength there should be, again obtained by laying up or repairing that. So a role of design is also there to really calculate. We have to provide them input as an inspector. What are the damage and what extent damage is by using various NDT methods. And based on that, repair scheme is prepared and utilized. So this is a quite a lot area. MRO, especially MRO people, they do a lot of work on that and need training on that. So this is from my side. I think
Thank
you
you.
have to, the person have to learn a lot on that, right?
Absolutely. Okay, so with that, I think we come to the end of prepared questions. We have quite a few questions, and I'll open it up to any panelists. The first question is, which composites can be used in remote control planes? It's open to everyone.
See, plane, whatever is there, is not a specific to a remote control or not remote control plane. It depends on what kind of path it has to follow, where it's going to work, which environment is going to work, what different feature it needs. Accordingly, that composite is selected. Is not a, you cannot say any thumb rule that we have to take carbon, glass, or Kevlar. Depend of the condition where it is flying, depend on its usage. All those things are important part of that. But maximum people are using for structures carbon because of a high fatigue strength. But if it impact strength is more that particular area, we have to use Kevlar. So depends on the requirements. We are using various kind of composite, whether controlled by human being or not, are controlled remotely. Both the things, whether remote control or manual control.
Thank you, Dr. Krishna. Okay, the next question is, what are the disadvantages of composites in terms of its effect to environment, and how is aerospace industry handling it? Naveen, I think
I
you
can
touched
take
upon it. Do you want to take that?
I can take the next two questions maybe. So the environment effect is a big effect, as I mentioned. Uh, that I would say at least there are two parts. One is when you analyze as a load, that means the thermal mismatch I was talking about. With if you're metal component attached to a composite, or if within composites too, you have different composite components coming. Or if you have high temperature application, then also you have to consider the delta temperature effects and the moisture effects as well. So there is load side of the environmental effect, and then there is a allowable side of the environmental effect. So there are two different ways you can at least consider them. So one is when you do like a finite element analysis or hand calculations, then if you go back to your hydrothermal analysis, then you can use that delta T as a load. And then when you look at the margins of safety, then the allowables we get, which is typically what we do in most of the aerospace, typical commercial applications, typical, I would say, uh, that we knock down, it's called knockdown factors. We knock down the allowables by a certain amount to take care of the environmental effects. For example, I'll give you a simple example. We test the tension coupons or compression coupons, two big ones, tension and compression strength, in room temperature as well as at a high temperature with moisture absorption, something like 180 F with 90-95% humidity. It's called elevated temperature wet, ETW. Different people use different terminology a little bit, but it's basically elevated temperature wet allowables versus the room temperature dry allowables. So you see the difference and you take a knockdown, and those are the ways actually to take care of those environmental effects quickly. All right.
I think if you can take up the next one as well, that would be great. What failure criteria is used for composites? How different is PU PUC criteria different from Hazine criteria?
So the failure criteria, as if you start looking into the various books, there are various failure criteria. I mean, a lot of people even use von Mises. I don't know why, but people use it for composites. But the key failure criteria is most widely used are either max strain, max stress, or one of the quadratic failure criteria like psi, wu, psi. That's one of the most used ones. Puck and Hashin criteria, which you're talking about, are used, but most of the time they are used for progressive failure analysis, not for like designing quick structures. Because when you're designing, structures for damage tolerance or effects or defects and things like that, and including environmental effects, you get your max stresses and strains in the ply, and you end up applying a max strain or max stress criteria, and which gives you an answer pretty quickly. But if you are looking at fatigue life or effects of dynamic stresses and things like that, and failures, then some of these Puck, Hessian, or there are many other criteria. Hamada Sun comes to my mind, and then there is NASA has developed LARC criteria. There's so many of them there. Those are mostly used when you're doing if you heard of PDA, progressive damage analysis or progressive failure analysis, which means you are kind of studying the damage progression when you're analyzing the structure. So that's hopefully that answers your question.
Naveen, the next up is a very interesting question. How composite materials on a fighter jet are able to absorb radio signals from enemy radar? What are the stealth coatings that are used essentially? The extension of that question is, why ferromagnetic particles are used in aircraft body? Mr. Narayanan, would you be able to take that?
Yeah, I have no big experience on that. But one thing is, if you use composites are usually used in radome covers, radomes. They are the purpose is to become transparent to radio waves, not for stealth.
Yeah, so I think the question was specific to AMCA program or LCA fighter program. How do we achieve stealth features? And especially if it's a 5th gen fighter, it's got to be a stealth jet. So how do we achieve stealth essentially?
Stealth depends on design. What way you're designing when your radar waves are coming there, you should not go back to the radar. It should get reflected or diffused or absorbed. So there are various techniques are there basically. One is how you're designing your structure. If you see LCH, the design is there. Another is there some coatings also available there who are using for stealth, and but their role again is there. Whether they will absorb those waves or they will deflect in a different directions, diffuse them rather sending it back to the radar. That's the important part of is there. And some coatings are developed in India also, and people are trying to test it and see that to what frequency, because different frequencies are will be there. So this should be range is wide when frequencies are there. So how to take care of wide range of frequencies, because various instruments will be used to track your jet fighters. So the designer has to work on that on various frequencies, how is going to handle it. So accordingly, they will design the surfaces and use the various kind of coatings also wherever required. So that is itself is a quite big area to understand that. And then this will be used, and people from different countries also what they're doing development design it, try to understand that and utilize in MCA. So those things will be done in MCA also. This ADA and all, they will definitely will try to find out those different things from other countries also and try to implement, and or they will study the aircraft like Su-57 or F-35 and all, and try to understand their structural design part to implement in MCA projects.
Thank you, Dr. Krishna. If there are any other questions, we can take one more question at this point in time. I don't think we will be able to take any more questions. But otherwise, thank you, everyone. I really appreciate your time. And if you really want to learn more about composites, you want to build your career in composites, we are launching the next batch of our composites course, which is starting from 17th of January. And all of the panelists who are on the call right now would be the experts. They've got decades of experience building composite structures or designing them. So we'd love to have you as part of our batch. Our registrations will close down very soon. We don't have a lot of seats left, so I would encourage you to participate in the course if you want to build your career. There's one more last question. There is someone who's saying, I'm working as a composite tooling designer. How do I switch to a part designer?
I can take it a little bit. So tool design is its own specialty, I would say, because tool design can also use composite material. There are tools which are made out of carbon fiber as well. But most of the tools are made out of either aluminum or invar. So, I mean, at the end, you're designing the tools mostly for temperature effects and, the spring back and things like that, right? Because it's pretty much either going into the oven or the autoclave, or if it is on a room temperature, it's not doesn't see that kind of an environment anyway. But when you switch to part design, then that's where I was talking to earlier is about understand the theory of composites, mechanics of composite materials, understand all the plates and shells analysis and theories, and starting from basically if you're already into engineering, strength of materials, and go on from there. So learn those things, learn all the mechanics of composite materials, take some courses, as again Hardik has been talking about. There are many courses AeroDef offers in that direction. So you can take some of those courses, because if you already have a background in tool design and analysis and engineering, I'm pretty sure you will be able to catch up pretty quickly and get into the part design. Now, design also, there is a CAD part of it and there is analysis side of it. They're two different things. But if it is a CAD part of it, you already know the CATIA or some of the Autodesk or whatever software SolidWorks is using. But if you get into analysis, then you need to learn, obviously, more advanced tools like Nastran and Abacus and things like that. I hope I answered your question.
Thank you. Thank you, everyone. Really appreciate your time. I hope it was of value to you, and do reach out to us. We are happy to answer any additional questions that you have, and we would love to see some of you in our upcoming training batch. Thank you, everyone, for your time. Have a great day.
Okay, thank you.
Thank you, everyone.
Thanks.